Hey, what's up? So today I want to talk about algorithms. And I really think algorithms are like one of the most beautiful things invented by humans because for one, it's just so elegant. So I was recently reading about a story where a guy lost his cycle and then he goes to the police to find his cycle. And the police goes like, "Oh, there was a CCTV there, so we can go and like watch the footage and see when it was stolen." And so they go take the CCTV footage, but the footage is too long. It's like 40 hours of random road pedestrians crossing around, and they see his cycle come around, and he parks his cycle and he goes somewhere, and he keeps there for like a couple days. So they don't know at what point that the cycle was actually stolen. And the police says to this guy, "You know what, it's going to take a long time for me to see. It's very infeasible for me because I have to sit through like 48 hours of footage." And the guy was a computer scientist, so he just tells the policeman, "Just go to the middle part of the footage and just see if my cycle is there. If it is there, then you don't have to see the entire thing." And the policeman goes, "Oh yeah, that makes sense." And he goes to the middle, and the cycle is still there. So he goes to this from the middle to the end. There is basically 2 hours of, I mean, 2 days of content becomes like a one day of content. And now again he goes to the middle and like it splits, and now the cycle is not there. So it means the cycle was stolen between day one end or day two, second half of like first half of day two. And now it splits, and now it is very easy to find out when his cycle was stolen. uh, that's basically fucking binary search. You are either going left or right until you get the key, and once you get what you're looking for or the key, and you basically find out in a very less time, if you rather than searching it manually, searching it one by one. And I think that is one of the most beautiful things. uh, I know it's like very basic in computer science, like binary search is like one of the most basic things like every first year will learn. But then I still believe that is it's so essential to how entire algorithms and entire optimization algorithms work. Let's take disks for example. I also learned this very recently, uh, and it like kind of blew my mind and how elegant and simple it was. So disks are basically finite, so they are like round in shape, and they have like a head that is pointing to their whatever, the tip of the thing. That is how they read the data basically. So when you store something, the tip of the whatever the handle actually moves to a certain part of the disk and writes your data there. And when you're searching through this data, it can be very time consuming. It's totally different from RAM, where you're just accessing memory, but you're not accessing like storage memory. So when you're accessing a data from disk, it takes a lot of time. So every program, whenever you write code, the variables that you're fetching and variables that you are comparing with each other, they have to be fetched from the disk, and then compared, and then manipulated. Look, maybe you want to add a number or a subtract number, and then sent back to the disk. So this taking from the disk and sending back to the disk takes a lot of time, and it is not something that can be very simple. Like, okay, I kind of fumbled there, but it you have to really make it efficient so that you can minimize the amount of time that the disk actually takes. So how do you do that? Well, binary search, right? Binary search is the most simple answer because that is the most easiest way. You sort all the data and then you put it in a binary search and you can search it easily. Well, it's not that simple because binary search, it just means you have two options in each position. Either you go left or right, or that itself is the thing that you're looking for. So basically, binary search means you store data in levels, and these levels can explode very easily if the data is a lot. Uh, it increases exponentially, so I mean, it increases logarithmically. So if you have two sets of data, it's like maybe like two rows. If you have like four sets of data, it's like maybe three rows. And if you have like 9 or 10 sets of data or 12 sets of data, it goes to four rows. It does increase, but it does increase in a logarithmic way. And when you have large amounts of data, you have like gigabytes of data, you can't really store that much in a disk, and it will obviously run out. Or even if it doesn't run out, it's a really inefficient way of storing, because you have to keep splitting. You have to The disk keeps moving every single point of the node. So now, what computer scientists have done, like I'm paraphrasing this entire thing. It's not like actual stuff. I'm just paraphrasing from what I've learned, which is pretty amazing. The thing that I've learned, I mean, so disks are divided into blocks, and these blocks have a certain like limit to how much they can store, and it makes it easier so that one block is right next to a different block. So when the disk needs to move from one block to another, they just have to go sequentially. They can't like skip blocks, because the disk is a physical object and you can't really skip physical objects like you can do with software and like you mental things. So each block has a limit, let's say like 1 MB, 2 MB, 1 GB, 2 GB, whatever. And in that block, I can store a bunch of shit. I'm going to store my bunch of data there, and I can basically, if I know which block I have to go, if I know which block my data is in, I just have to move to that block and take my data. So that is very simple. But now, how do I know which block it is? Which is where indexing comes to play. And indexing is basically you add an index or like a pointer to where the actual memory is there in the disk. So that's how you do it. Now let's say there's like a set of 10 people, and each person gets an index. I am index 1, and my neighbor is index 2, you are index 3, and whatever. So if I need to find you, I just need to find where index 3 is, because that is your index. I just need to know where index 3 is, and once I know where index 3 is, that index will just point me to your home, and I can come to your home. I'm like, oh, hi bro. So that's just basically how indexing works. And index can be as simple as just a number, which takes only like 4 bytes, as opposed to your data. Your data means every single gene in your body. I can take that as data. That's maybe like fucking 45 terabytes or something. And I don't have to search for 45 terabytes. I just have to search for the 4 bytes that indicates that it's you, if that makes sense. 4 bytes that indicates that it's you. That's your identification number or whatever. If I know that, I know everything about you. So that's basically how indexing works. Again, I'm paraphrasing it. It might not be actually like how it works and all, but that is just my understanding. So I use this index to find people, and now index can also grow, right? Index can also be like, say I'm having a database of a 1 billion people. I'm having database of like every single human being in this planet, like 8 billion people. So I need to have 8 billion indexes. And if I'm storing it in a single disk, I can't obviously store 8 billion fucking indexes. I mean, I can store them sequentially, but if I have to again search for it, I have to put them in like a binary tree or something that makes it easy for me to search. And again, if, let's say I use binary tree, I have to go through, let's say I am searching for the last number 8 billion, and the root of the node is 4 billion. So I have to go to the end of the right side. I have to go to the last row or the last level of the right tree to reach the 8th billionth whatever index. That's when I know where the 8th billionth person lives. So that means I have to read from a disk a lot of times. I have to go so deep. I don't know, let's say like I have to go 25 levels deep. I don't know if 25 corresponds to like fuck it, but I have to go 25 levels deep. So that means, remember when I said disks, I can't really like manipulate or compare data directly. I have to read from disk to memory, compare, and then write it back to the disk. So that means I have to read it 25 times, compare it 25 times, and write 25 times till I find the last level. So traversing through the depth in a binary search tree is very expensive. I mean, not expensive, but like a bit time consuming. But that is the best we have got, right? Now, if you are doing it like in a selection sort, which means I go to the first one, see if it's 8 billion or not. It's not 8 billion, so I go to the second one. It's 8 billion or not. It's not 8 billion. So I go all the way till 7 billion 999 million 900 whatever. I have to go till there and then go to the next one to find 8 billion, which is a lot. So the best option we have is binary search, right? Now, these people, these mathematicians or like computer scientists, these smart people have devised something known as a MRE search. So binary is for 2, So MRE is for however much M is. I can put M as like 5 or 6 or 7. So that means one single node will not split into two, but will split into like say 10 or 15. And that is one of the most beautiful things, because that means not only I have to only search very less and to again go logarithmically. Like I won't exponentially grow my search. I won't like linearly grow my search. I'll again search logarithmically, but also I have to travel less levels. Now, let's say I have 8 billion people, and then I have like 20 or 30 elements in a single node, and I point to 25 more levels in a single node. Not I'm not saying each node. I'm not saying the total nodes. I'm saying each node points to like about 25 different nodes in the second level, and that points to 25 different nodes in the third level. So that massively shortens my need to search till the end. Now, if I need to search till the end, maybe it's like 4 or 5 reads. That's it. I don't have to read like 50 times to reach the last element. I just have to read it like 5 times, and I'm still going logarithmically. I'm not going. I'm not doing linearly or like something inefficient. I'm still doing it efficiently, which is pretty great if you ask me. And I like I really hope I can like show you some diagram or something, but uh, what I explained right now, MRA tree is nothing but a B tree, and B tree is used for storing indexes. So index is nothing but something that points to the data, and we store the indexes in such a way that it's easy for us to find the index itself. So once we know the index, we can automatically get the data. And now, how do we store the index? Let's say I have like 20 indexes that I have to store, and I start building a tree. So I put the first index first, second index second, and third index third, obviously. And let's say I have a B tree with maximum 3 nodes, 3 elements in a single node. Then I can point to 4 nodes. So anything, let's say I have 10 here, 5 here, 15 here. So anything less than 5, I store it here. Anything more than 5 and less than 10, I store it here. Anything more than 10 and less than 15, I store it here. And anything more than 15, I store it here. And here I have 1 to 5 elements, right? That I can again split into 3. Anything less than 1, I can store it here. Less than 1 to 2, I can store it in between here, and so on and so forth. Now when I need to find 20, 20 is the biggest element that I need to find here. I just check the first node. I see, oh, it's greater than 15, so I move to the rightmost node. And the rightmost node has 16, 17, 18, 19. Or at least have 16, 18, 19. Okay, it has 16, 18, 19. Now where do I go for 20th? I see, oh, it's greater than 19. I go to the third node, and I just find it in 3 nodes. Now if I have to do the same thing in a binary search, again I can find it easily. It's a logarithmic search. I just have to compare. If it's bigger, I just have to keep going, and I will do it. But I will not do it in 3 reads. I will take probably around like 5 or 6 or 4, I don't know. But this is just for a small example. Now if I do this for a large set of data, a large set of indexes, that's going to be crazy, a massive save for me if I ever want to do it, uh, which is amazing. Which it just blew my mind when I was reading about this. And I know I might just be like kind of overreacting, but B trees are so cool, bro. B trees are so fucking cool. And yeah, and there's this improvement on B trees called B plus trees, where each element does not store the index directly. It just stores the pointer to the index, and then in the last layer we have the actual index that points to the data. It's a bit confusing, but then that is also a massive improvement when you have sorted data or categorized data. uh, yeah, man, it's crazy. And the last layer is connected to each other. So when you go to the last layer, you'll see a single list. You'll see a single list of data. Where if I go to the first left side, I go to the end of the node, I go to the first index. Now I can go to the last index. I don't have to come back up and then go down. I can just traverse it linearly, and I'll reach the last index. That is also such a great improvement. It just blows my mind. And that's how, like, databases are made. That is how I think SQL works on B plus trees. I think Postgres also works on B plus trees. I might be wrong, but most databases, most things that deal with disk reading and stuff with persistent memory use some sort of optimization strategy like B or B plus trees, which is one of the most craziest things. And I didn't even plan on talking about B plus trees in this video. I just wanted to talk about algorithms in general and how algorithms like influence real life, like seating algorithms and sorting algorithms in exams. Like, you have entrance exam, and fucking algorithm is going to decide what college you get when you enter it, and there's like a lot of criteria, and it's all done using algorithms. And not only that, the city that you're assigned, or let's say fucking Tinder, for example, you left swipe, right swipe, even the people that you meet on the internet are mostly decided by algorithms, which is pretty crazy. That's what I want to talk about, not B plus trees, but B plus trees are so interesting. I just read across them. I had it in my syllabus. Okay, I had it in my college syllabus. I didn't pay attention then, and recently I just was coming across this concept, and B plus trees are amazing, dude. That is all I want to say. Um, I don't know. I'm in love with B plus trees. I would marry them if I had to, because they're so elegant and so beautiful. So that is what I want to talk about. Yeah, man. I, yeah, I might talk about something else interesting in the future, but yeah. Thank you. Um, okay. How do I stop this? Oh yeah. Bye bye.